Hi there, I'm Louis. Today we'll take a look at Conway's game of life. It is one of the most famous examples for a cellular automaton. Cellular automata are computer models that are mostly used to study complex systems, emergent phenomena, and self-organization. In the case of Conway's game of life, we start with a 2D grid of cells, where every cell can hold a value of either 1 or 0, or you could think about it as living or dead cells. Every cell will then change its state based on its own state and the state of its neighboring cells. By applying the rules over and over again, this will evolve over time and will create interesting and emergent patterns. Now let's have a look at how this works exactly. So we'll start with a grid, and we'll give each cell an initial value of either 1 or 0, in this case randomly. And now every cell will take a look at its 8 neighboring cells and sum up all the living cells around it. Now one important thing to notice is that the cells at the edges actually don't have 8 neighbors. So to circumvent problems here, we will wrap around the edges. This means that cells at the edge of the grid will use cells on the opposite side of the grid to fill up the missing neighbors. Now the rules are fairly simple. We can visualize them as a decision tree. Every cell first checks if it's alive or dead. If the cell is turned off, we want to check if it turns on, so basically if it's gonna be born. And this is the case if the sum is exactly equal to 3, otherwise the cell will stay dead. Now if the cell is already alive, we want to check if it's gonna die. And that is the case if the sum is less than 2, so basically it's going to die from underpopulation, or if it's greater than 3, so the equivalent to overpopulation. This means anything in between, so 2 or 3 neighbors, leads to the cell staying alive. And those are actually all the rules you need for these interesting structures and patterns to emerge. So let's get started in Blender. First, we want to add a new geometry node system. And we want to start with a grid. For now, we can set this to 20 by 20. And now we want to set up the grid properly. Because at the moment, if I visualize the indices here, you can see that the indices are running along the y-axis here, but we want them to be corresponding to the x-axis. I will explain why in a moment. But for now, let's add a transform geometry node and rotate that by -90 degrees on the z-axis. So it's oriented like this. Now because we rotated the grid, our inputs for the grid are flipped. This means the vertices on the x-axis are responding to the vertices on the y-axis actually, and vice versa. We will now add 2 integers as our width and height input, so we will have to keep this in mind. I like to turn on snapping in the upper right corner here as it helps me to stay organized. Let's now rename those 2 integer inputs. The first one will be our width and the second one will be our height. So now this will go in here and this will go in here. And we can now set those back to 20 by 20. I can also delete my index visualization here, and now we can start with defining the neighbors. So first we want a system that procedurally adds some attributes that will store the neighbor indices. At the moment Blender doesn't support arrays or lists. That's why we have to store the neighbor indices onto individual attributes, but we'll build a system that deals with this automatically. So the base for our workaround here will be a repeat zone that will add a new attribute every iteration and fill it with the corresponding point neighbor index. We want 8 iterations because we know every point has 8 neighbors, so we want 8 repetitions as well. So the first thing we need in here is a store named attribute that will save a new attribute every iteration. This means that we need a new name every iteration as well. And to do this, we'll start with getting a string in here, then a join strings, and then a value to string. And what's still missing now is an iteration counter, so we need a math node as well. Now let's grab a new input from the repeat zone and plug it into the math node. Set the add to 1 and then plug it into the output of the same value of the repeat zone. Now I like to label this add node as I++, just because I like to pretend that Blender has a working for loop. Anyway, we can now use this value to drive our value to string and combine it with another string as a prefix. I'll simply call it n for neighbor. So if we now plug this into the name of our store named attribute node, we will create 8 new attributes named n0 to n8. And as you can see right here in the spreadsheet, this is working perfectly. Let's quickly clean this up a bit. Also, we can make this iteration to string setup into its own little node group. Now I'd like this prefix input to be exposed, so we can create a new input here by dragging from the group input into the join strings and delete the string node. This has no input value. We have to disable the height value in here so that we can type in here. So let's put our n in here and it's all working fine again. Now, every iteration, this will add the next neighbor attribute. And now every iteration, we want to fill the attribute with the correct neighbor index as well. So let's switch this to integer. Now comes the complicated part. So to define our neighbors, it will be easier and more universal if we mapped our grid here to a coordinate system. This will make defining neighbors a lot easier, allow easy wrapping of the edges, and make this a lot more flexible in general for future setups. We will convert our point index to a coordinate, then we can easily define our neighbors using a simple offset coordinate and then convert them back to the corresponding point index and then save this onto our attribute, so our fake array. Let's take a look at this using an example. We'll take a look at point 45 and a width and height count of 10. Getting the x coordinate is quite straightforward. We take the index modulated by the width count. The modulo operation basically gives us the remainder of dividing the index by the width count. It's like counting how many cells are left after we fill up each row completely. To get the y coordinate, we have to divide the index by the width count and floor the result. It's like figuring out which row the cell belongs to. The whole number part of this division gives us the y coordinate, that's why we have to floor it. To convert this back, we basically have to reverse this. This means that we will multiply the y coordinate by the width count and then just add the x coordinate. Now let's actually implement this. As we just discussed, the x coordinate is the index modulated by the width, so we can now add an index node and also a math node. And let's set this to truncated modulo. Now hook up the index and width. We can now copy this and use it for the y-axis as well. And the y-axis is a floored division, so let's divide this and then floor this. Also by the width. So let's get this over here. And we can now group this. So this goes in here, this goes in here, and this is our x and this is our y coordinate. And in here goes the width. And now we can jump back up. So let's name this to index to coordinate. And now we want to define the offset. So we need 8 vectors that point to our 8 neighbors in the coordinate system. There are 2 basic ways for how we can do this. First, we could make a list, for example by using an index switch and typing in every vector by hand, which can be quite tedious. The alternative way would be a procedural approach, which probably takes the same amount of time but is a lot more fun. I'll start with one of the corner vectors, like -1, -1. Then I will rotate this vector around every iteration by 1/8 of a full rotation. And as the last step, I will round off those vectors so they are snapped onto the grid. So back in Blender, we'll add a vector node and a vector rotate node. Then type in the starting vector, in my case -1, -1, but you can use any of the corner vectors. Then we'll connect this to the vector rotate node. And now to define our angle, we'll use the iteration counter up here and plug it into a divide and divide it by 8. To make this into fractions of a full rotation, we need a multiply here and multiply it by pi times 2. Now we have to round this, but as I found out, Blender doesn't have a round function in its vector math node, which took me way too long to figure out. But this means we have to build our own by using a separate XYZ node here and then rounding the components here individually using a normal math node. After this, we can recombine them using a combine XYZ node. I'll also now group this and make sure that the output is connected. And let's also make sure to rename this to round vector. This one went straight into my asset library, as I think it should be a basic functionality in Blender. Let's now clean this up a bit so it's a bit more concise. We now have to separate this again, as we have to access our coordinates individually for the back conversion later. So this will be our offset. Let's group this, and we can put this in here, and let's name this also. So this is our X offset. This is our Y offset. Now we want to name this. This is our calculate offset. And also I forgot to name this. So let's name this iter2 string. Okay, so now we have all our components here. We have our X and Y coordinate and our offset. Now all we have to do is add the offset onto our coordinate. So let's grab a math node and add the X offset to the X, and then the Y offset to the Y. Because we want to wrap this around, we have to handle the cases where our coordinates exceed our coordinate system. To prevent this and to wrap this around, we want to add onto here the width, and then use a truncated modulo and modulate it by the width as well. The modulo makes sure that the new coordinate won't exceed the boundary of our grid by looping the coordinate around. We add our width before that to handle the cases where the coordinate would be offset to a negative number, as the modulo operation only works on positive numbers. And now for the Y, we want to do the same. So we can just copy this, but we want to use the height here instead of the width, because we want to wrap around the Y axis. And we will add the height here as well. So this takes care of wrapping around the edges. And I'll again clean this up a bit. Now that we have our offset coordinates, we want to revert them back into an index that we can sample later. To do this, we have to multiply our Y coordinate by the width, and then add our X coordinate onto that. Now we can store this onto our neighbor attribute. And if we check the spreadsheet here, this now fills out all our neighbor attributes as it should, and also seems to be wrapping around. Okay, so this is our basic setup done now. We can now select all this and group it. Unfortunately, our group inputs are not labeled at the moment, so let's fix this. This is our width, and this is our height. Wonderful. Now we don't need those inputs anymore, so we can delete them and just type our inputs in here. Now there's still something missing, because we don't have control over the size, and our aspect ratio will get squished if we don't use identical inputs. So let's quickly dive back inside. Let's fix the aspect ratio first. I'll use the width as the base reference, and I will adjust the height accordingly. So to get the correct aspect ratio, we have to divide the height by the width, but we have to remember that our length is 1 unit less than our point count. So we have to subtract 1 from our height and our width before we divide it. So let's bring in a subtract node and subtract 1 from the width. Then let's copy this and subtract 1 from the height as well. Now we can do the division and divide the height by the width. Now we can plug this into our height length, which is the size X, because we rotate our grid afterwards. And as you can see now, the distance between the points stays consistent and nothing gets squished. Now we also want control over the size, and for this we can add a multiply here and connect that to a new input. This will be our width length. Now let's check if this works. And that's not working correctly. Let's check back inside what's missing here. Yes, okay. We of course also have to feed this into the size Y, so that our width actually also gets scaled along. And this now seems to be working fine. Let's name this generate game of life grid. Okay, so now that we have our grid set up here, we can finally start with implementing the simulation and rule system. So let's drop in a simulation zone here and hook that up. And all we need in here is a store named attribute, so we can update the state of each cell every frame. And we'll need another one in front here to initialize a value. So we'll name this state. So this is a Boolean, and we can use a random value with the type set to Boolean to set an initial state. Now if we check this using the viewer node, we can see that this fills every cell with an initial value of either 1 or 0. Now we can start with implementing the rules. And as I mentioned in the beginning, every cell will look at the summed states of its neighboring cells and compare it to certain parameters that we will define. Let's start here with summing up the neighboring states. For this we'll use a repeat zone again and set this up in a quite similar fashion. So this will be our I++ again. And we'll go in here. We can now reuse the iter to string node that we created before. And let's quickly delete the geometry stream of the repeat zone in here. For that, go to the N panel, to the node section, and just delete the geometry input, as we don't need it. So this will be 8 iterations again. This value we can set to integer, but it's not needed. But I would consider it good practice. Now, because we want to sum up a value, we need a math node here. And this will repeatedly add up the state of the currently read neighbor cell. So let's hook it up to new input of the repeat zone and plug it into the output as well. And for clarity, I'll rename this to sum. And let's set this to integer as well. Now, because we want to access the neighbor attributes, we need a named attribute node. And hook up the iter to string node here and type n into the prefix string here. If we now hook up the iteration counter to the iter to string node, this will loop through the neighbor attributes and spit out the corresponding neighbor indices that we can now sample using an evaluate at index node. We can now plug this into the index and then add another named attribute node with which we then can sample the neighboring states. Now plug that in here and let's set this to Boolean. If we now plug this into our add node here, this will sum up all the neighboring states. And now we can group this. And in here, we only have to plug our sum value into the group output. So this will be our sum neighbors. And let's also specify our attribute name here, which is state, and also switch the type to Boolean. Now what's actually left is implementing the rules. So for this, we first want to check if our currently checked cell is alive or dead. So let's grab a named attribute node and select the state. And this will now drive a switch node that we set to Boolean. We use the switch node here because if a cell is off, we only have to check if it will be born. And if a cell is already on, we only have to check if it's gonna die. The condition for a cell to be born is if it has exactly 3 neighbors that are alive. We can check this by plugging our sum here into a compare node and checking if it's equal to 3. And this now belongs into the false input of the switch. And now the alive cells will only stay alive if they have exactly 2 or 3 neighbors. So we can now copy our compare node here using Ctrl+Shift+D so that our inputs stay connected. Now copy it once more and change one of them to 2. These now go into the true state of our switch. And to combine them, we can use a Boolean math node that we will set to OR. We can now drop this in here and hook up both our compare nodes here. We can now plug this into our attribute, and this is it. We can quickly check if this is working using the viewer node. Let's copy our attribute node over here and use the Ctrl+Shift click to connect it to the viewer. If we now let this run, this should be working. And it looks like it's working fine. To make this a bit more visible, we can use a mesh to points. We can also up the resolution now. So go over here and I'll go with 150 by 150. Wonderful. Now that our simulation is working, we may also want to render it. There are 2 basic ways to do this. We could either just render it as points, or we can instance some squares onto it that will display our simulation. In both cases, we will want a correct scaling of the cells, so let's quickly implement this as the last step. We have to dive back into our grid generation, and we'll need a divide node that we can just copy from here. And now we have to divide our width length by our subtracted width count. We can now connect this to the group output and rename it as well. Let's name it point scale. Now to render it as a grid, we'll need a instance on points node. Let's get rid of this mesh to points node here and instead hook up our instance node here. As the instance, we'll pick a grid node here, set the vertices to 2 and just connect it to the instance input. Now we have to feed our point scale into our instance scale. And to actually see our simulation here, we have to switch the view node from auto to instance for some reason, because it doesn't automatically detect the instances. But playback with a lot of instances is always slow anyway. So we'll use a realize instance node here and switch back our view node to auto. Now let's get to rendering this. This can be done quite easily. First we need to add a set material node. Let's set it to the standard material and open up a shader editor here. Let's home this. And we don't need the principal BSDF, and also to see what we are rendering, we have to turn off the view node here and switch to the rendered view. At the moment this is obviously black, but we'll start with a emission shader and connect that. And now to display our simulation, we need a attribute node that reads out our state attribute. So let's get that in here. Now specify our state attribute. Now we can just hook this up to strength. And as you can see, this is displaying fine. We can make the glow here a bit stronger by adding a math node and setting this to multiply. Multiply it by something like 4. This can be easily rendered in Eevee, so we can switch to that. And I like to turn on bloom. I will dial back the intensity a bit. Yeah, like this. And now with this, we are done. Feel free to experiment with the setup. There will be a second episode to this, where we explore how we can make the rendering more interesting by adding a fade-off value, and how we can actually interact with the simulation by introducing different modes of input. I really hope that you enjoyed this video, and I'll see you in the next one.